the last class, we have discussed about the Flory theory for the good solvent case and the bad solvent case, and we have got the scaling relations. And then towards the end, I discussed about the self similarity of the polymer chains and the fractal nature, and that is where we were. So, we said that the number of segments at a distance r does not go like r to the power d as for a solid object, d being the dimension we are working in. So, if it is like a solid rod or a disc or a sphere, we basically have the scaling relation for the number of segments at a distance r, within a distance r, to be like r to the power d. In the case of a polymer chain, it is not true. We can have m going like r to the power some other power d to the power f, where d to the power df is not equal to d, and if that is the case, we call this a fractal. Okay. So, we have done this briefly for the 3-dimensional case. So, what I will do now, I will do a Flory theory analysis for a general d-dimensional walks for different cases. We already did for ideal chain, we have done the 1-dimensional drunkard walk, 2D walk on a lattice, and the 3-dimensional or a general z-dimensional walk, and we have found that the scaling relation is unchanged. So, now we will do it for the case of the self-avoiding walk and the collapsed chain that we see in the good solvent case and the bad solvent case. Okay. So, and then we see like how the fractal dimension of these walks depend on the dimensionality. So, let us get started with the self-avoiding walk in d dimensions that we get from Flory theory. Again, the Flory theory basically refers to the idea that the contributions of energy are additive, and then we take the elastic energy as that of an ideal chain. The excluded volume energy, we take it as of a segment gas where concentrations are uniform, and not all theories of course are done by Flory himself, but these basic assumptions are what is referred as Flory theory in literature. Okay. So, let us look at the self-avoiding walk for the case of V higher than 0. If you recall, we look at the competition between the elastic energy and the two body interaction, assuming that the higher order interactions in concentrations are smaller compared to the two body interactions. And essentially for the elastic energy, we are using the relation we derived for the ideal chain case, and for the interaction energy we start from the virial expansion, keeping only the first term, and then we assume that the concentration is uniform in the volume. So, now the analogous quantity of volume in 2 dimension would be the area, in 1 dimension will be the length. In general, we are interested in the number of segments in r to the power d, because r to the power d is the relevant volume or surface area or the length depending on the dimensionality we are interested in. Okay. So, now my u due to the excluded volume can be written as by the scaling relation. So, d of r integration goes like r to the power d. So, in one dimensional I integrate along only one coordinate. So, we have integration of say dx. So, the unit is r. If we are in two dimensions, we integrate in dx dy. So, unit is r square and so on. So, in general integration over dr has a dimension of r to the power d. In any way we assume the concentration to be constant. So, then we have V kBT m by r d squared, and so we get this, and so the total energy is the sum of these two, elastic and interaction energies, which now scales like kBT multiplied by r square by mb square plus v m square by r to the power d. Now, I will again use the same idea that we have used for three dimensional case. We take the minimization of this u to get the size. So, we get dou u by dou r is equal to 0. Using the u that we have derived, this becomes again I am dropping the coefficients since we care only about the prefactors. So, we have this, and using that we can get r to the power d plus 2 scales like v to the power and just v and m to the power cubed, and so we get r scaling like v to the power 1 by d plus 2 m to the power 3 by d plus 2. You can verify this by putting in d equal to 3, and we get the relation that we have got for 3 dimensions. Okay. So, now since the fractal dimension df is defined in this particular way, what we get from here is df is equal to d plus 2 by 3, and we can see like what it becomes in different dimensions. So, like for the case of 1D, df is equal to 1, that is same as dimension d. So, in that case it behaves like a solid object, and you can see why this is the case, because imagine a walk in one dimension that is self avoiding. What it means, if you remember the drunkard walk idea, that the drunkard can only walk either to the left or to the right in all the steps, because every time he makes an opposite move it will lead to an overlap. Okay. So, essentially in this case what we recover is the relation we derived for a rod. So, the distance travelled by the drunkard will be scaling like the number of steps. Okay. So, in this case it is not a fractal. However, if we have 2D, then we get df equal to 4 by 3. This is a fractal. So, now you can see in 2D we do not need to be like avoid any direction. He can move in both x and y, still avoiding an overlap. This, for example, contains steps which are both in the x and y directions and both in positive and negative directions, but still it is self avoiding because there are no overlaps of steps. So, this is a fractal, and for 3D of course df is 5 by 3. So, since we are departing from the Euclidean idea of dimension, a fractal dimension is like a fraction really. So, it is very difficult to think in terms of an actual dimension that we are used to seeing. So, it is not a one dimension space or a two dimension space or a three dimension space. So, the derivations we are doing are for an arbitrary dimension d. So, we can plug in d equal to 4, 5, 6 whatever we want to. The assumptions made in the model will still hold in that particular case if we want to depart from the Euclidean idea of dimension. Okay. So, let us see like how it happens in the case of the poor solvent, the collapsed chain. That is when V is less than 0. So, in this case we assumed that the elastic energy is less than the two body interaction, and we also noted that we have to include a 3 body interaction just to make sure that R does not end up becoming imaginary, and we will make the same assumption here. So, U can be approximated by simply the excluded volume part, which again by virial expansion is this. Again we make an approximation that C of R is uniform and is equal to m by R to the power d, just like we did for the previous case, and we will be having, I will replace by the scaling relation and drop the coefficients. Which gives me so again we will make the same assumption about the minimization of energy to get the R. So, we have this which give rise to which in turn gives rise to R to the power d going like m, and what we do get if I compare to the relation for the fractal dimension, in this case we get df is equal to d. So, again this is not a fractal. So, just like we have derived for the 3-dimensional case, we can show in general that for the collapsed chain case, that is in the poor solvent when V is less than 0, the polymer chain is not a fractal. It has a scaling law same like a solid object. Okay. So, we only refer to the scaling law for this R or M. We do not talk about the structure of the objects. Of course, a polymer chain even in a collapsed state will have a different structure compared to say a metal ball. So, we will come to that later. All we are saying is the scaling law behaves similarly to a solid object. So, the relation that we have derived, the scaling relation, can also be useful in other cases. So, one particular example is the case when we think beyond a single chain in the system. Okay. So, if you think of an actual experiment, you do not have just one chain, you have an ensemble of chains present in the system. So, only in the very dilute limit you can have a situation that, let us say, if this is my solvent and I have polymer chains present here. So, in the very dilute limit, that is for very low polymer concentrations, we can imagine that my polymer chains are far off from each other, and each of them are following, say, whatever statistics we are assuming. So, let us say if we assuming the random walk statistics, that means we assume that it is an ideal chain. So, in that case it will remain an ideal chain only if we consider that there is no interaction between different chains in the system. So, only when they are like far off in the volume, they can show the scaling law for the ideal chain. So, for each of, in this case, each of them will show scaling law for the ideal chain if I assume that the system is in theta solvent or it is the V is equal to 0. Okay. However, if I increase the polymer concentration, eventually what will happen is these polymer chains will start to come together. Okay. And once they start coming together, they get like entangled with each other. Okay. So, a closest analogy one can think of is like a noodle. Okay. So, every chain in the system will be like a noodle piece, but then as they come together they get entangled, and in that case the polymer chain behavior is affected by the other polymer chains in the system. Okay. So, the overlap will start to happen at a particular concentration, which we can imagine in this following way. So, what we can imagine is, we can imagine that there will be a situation where the polymer chains are sufficiently close together yet not overlapping at certain concentration, and then after this point if I go to even higher concentrations, then the polymer chains will start to overlap, and then what we have is essentially an arrangement where you cannot differentiate where one chain ended, another chain started, like what you see in a noodle. Okay. So, as you raise the concentration, as you raise the polymer concentration, you see that in the very beginning it is in a range that is referred as a dilute solution, and then in between when they just start to overlap, it is referred as some semi dilute condition, and then at even higher value we have a concentrated solution. Okay. And of course, if I further raise the polymer concentration, we have a limit when the system only contains the polymer, it has no solvent. So, that will correspond to what is known as a polymer melt, that is no solvent or very little solvent present. Okay. So, let us say that there is some concentration, let us say C star, which we will call the overlap concentration, where this happens. Then for C less than C star, we are in the dilute range, and for C higher than C star, we are in the concentrated range. Okay. So, now when it starts to overlap, we can imagine that every chain is contained in a volume, and we can represent the volume by say an sphere, and then those volumes are just touching each other. Okay? So, there is no empty space in between, those volumes touch each other. That is, I can draw small volumes surrounding these each of the polymer chain. That is, anyway there must be a polymer chain also here and so on, such that within that small volume there is only one polymer chain contained. Okay, that is just a theoretical way to look at the overlap, but how it helps is it helps us to find the overlap concentration. Okay. So, these guys are often referred as a blob, where the blob may have different meaning in different context, but the idea is to show some kind of a confinement of a polymer chain or the segments of a polymer chain within a certain volume. Okay. So, at overlap concentration, blobs touch each other, and in that case we can think of that the polymer concentration in the entire beaker or whatever volume we are looking at is the same as the polymer concentration inside those blobs. Okay. So, there is one way to see that. So, let us say if I also think of like putting a blob here, then for the dilute case we can see that inside the blobs the concentrations will be higher, but if I look at say here or here any other vacant space, concentrations are very small. But once we go to the semi dilute regime, then in that case the blobs occupy the entire beaker, there is no vacant space left. So, the concentration inside the blob becomes the concentration in the overall volume, and this helps us to find the overlap concentration. Okay. So, and we know what the concentration inside the blob is, it is simply m by r to the power cube, and we know the scaling law for the r with m. So, let us say for the ideal chain case, r is going like m to the power 1 by 2. So, we can say C star goes like m to the power minus 0.5. Okay. We can extend the idea also for the self avoiding walk and the collapse chain. So, in general r is like m to the power nu. So, C star is m to the power 1 minus 3 nu, which is m to the power minus 0.5 for the ideal chain, m to the power 1 minus 9 by 5, that is minus 0.8 for the self avoiding walk, and it is simply 1 for a collapsed chain. And now you can see that since entanglements will start to occur beyond the semi dilute concentration, and the concentration at which the semi dilute concentration is achieved or semi dilute regime is achieved is given like m to the power minus 0.5 and minus 0.8 for the ideal and self avoiding walk cases, and we assume that m is much higher than 1. What it means is at very low concentration itself, because we are going about like 1 by m and m is already high, So, even at a very low concentration in physical terms like 1 millimolar or below, we start to see overlap of polymer chains. The polymer chains start getting entangled. The other way to think about is, although we have developed the scaling models for dilute solution, they can be very difficult to realize in the concentration ranges we typically are used to, that will happen at very small concentrations. Okay. However, if a chain is collapsed, anyway it is occupying very small volume, so the blobs will also be small. So, the condition when blobs touch each other and fill the entire space will take a higher concentration to reach, and that explains why entanglements will take longer time to happen in the collapsed chain case or in the bad solvent than compared to the case when we are in the good solvent or theta solvent. Okay. So, where we are now going is going towards the behavior of multiple chains. All the models we have done was for the single chain. So, now we are going towards multiple chain. What we will also show eventually in this course is we can start doing a thermodynamic kind of models or derive equations of states of polymer chains or polymeric systems, just like we do for other liquids and solids, and we will come back to this point later. So, I want to stop here and we will start with this in the next class. Thank you.